Okay. Okay, well, thank you, everyone. My name is Gil Speyer. I lead a scientific software engineering group at ASU, and I'm very glad to participate in the ResBazAZ this year. We're trying to think of an offering that might be of interest that sort of was unique, and I didn't see MATLAB on the agenda, so I figured this would be a good addition to the training offerings that we have there. Now, typically when I do this training, it's to the ASU research community, and so there was a lot of sort of cluster specific information in these slides. I've tried to purge most of those out, but apologies in advance if things are agave, which is our cluster specific. But I think this should have general appeal, not only for people who want to run on clusters, but there's actually information in here that may be relevant to those of you who are just running MATLAB applications on your desktop. So the overall outline here, we're going to just talk a little bit about the different computing platforms that are available in a centralized compute cluster, and go over what those are, because there's MATLAB offerings for a variety of different types of compute platforms. We're going to talk a little bit about MATLAB and what it is, and then the ways you might launch it. Most of the time, those of us who've just been using it on our desktops launch a nice MATLAB desktop. We run our code that way, and that's what we call interactive. But there's another way to run MATLAB, headless, if you will, like just basically just kind of submitting MATLAB jobs and letting them run in a batch mode on the cluster. And the advantage to doing this is that it allows us to submit large numbers of these batch jobs. So instead of, I suppose to do it interactively, you could open up, hundreds of individual MATLAB desktop instances, but it starts to become an absurd scenario. So what we do is we allow people to run batch, and then they can do these parameter sweeps and run lots of MATLAB instances across the cluster at the same time. Then we're going to talk a bit about how we might go a little bit deeper into our MATLAB code, looking at it, profiling it, seeing where there are opportunities to accelerate it. There's a multi-threaded version or implementation of MATLAB, which multi-threaded means that we're able to run lots of CPUs on the cluster simultaneously to do maybe a data parallel job, for example. And when we run in this multi-threaded way, the MATLAB way of doing this is something called par4. Although there are also, we're going to talk a little bit about what I call built-in parallelism. There may be parallelization already in your MATLAB routines you're running, and you're not even aware of it. And if you would only provide the platform for it to run on and maybe set a parameter like, parallel equals true, then you might be multi-threading with very negligible effort. I'm going to talk a little bit about big data support in MATLAB, but with distributed arrays and tall arrays. Tall arrays are a way of accessing really, really large data sets in files, but accessing them in such a way that you can bring portions of them into memory very easily. Then there's a batch submission, okay, but within MATLAB. So this is a slightly different from what I described initially. It's going to be about how do I submit jobs and use MATLAB as the one that submits the jobs and collects their results when they're done. Then we'll talk about GPU support in MATLAB. And then at the very end, I'll get into how do we write code, parallel code, whether it's in C and we're using OpenMP constructs, or maybe we're writing GPU code using NVIDIA's CUDA language, or anything like that, and being able to invoke it from MATLAB. MATLAB, probably some of you are familiar with what's called the MEX compiler, which is a compiler for code that can then be invoked from MATLAB. This is using the MEX compiler, but in this case, to invoke codes that have been written to run in parallel. So just a few words about what a computing cluster even is. You have wonderful compute resources there at the U of A. we have one and this is a picture of our cluster called Agave at ASU. Typically what we do is we log in from the internet into some sort of head node or login node where we launch jobs. We never run jobs on the login node, but we submit them to all the compute resources that are available there on the cluster. And these jobs will run as we can either run interactively or in batch mode. And then we're going to, and then I'll get into more about how these jobs will run. Okay, so there's two main compute paradigms that are supported for CPUs on a cluster. The one on the left is the one I'm going to really focus on here, and it has to do with what's called the shared memory platform. And what this means is we have a single address space. We may have lots of processors. Those are all those blue P's you see there at the top of that cartoon, but they can all access the same memory. And this is really a nice configuration to have, because if a processor wants to access anything in memory, it can see the exact same memory space as all the other processors do. And this is the space in which the PAR4 typically runs, not always, but I mean typically and best runs. So and some of these compute nodes, you on your desktop, you may have 4 CPUs or 8 CPUs, but on these compute nodes, you may have 64 CPUs. You may have enormous numbers of CPUs that you can use all at once to run. So, I mean, really what we're talking about is if you have a code that's only running on one CPU, you could theoretically and ideally, although very seldom in reality, be able to speed it up maybe 60 something times by running it in this way. The other configuration is, when we talk about a cluster having, 12,000 CPUs, those 12,000 CPUs can't see the same memory all at once. Then instead, what you might be able to do is if they're all networked together through message passing, you can transfer data between the nodes that have maybe 32, 28, 64 CPUs on them. And those messages are basically bits of data that are allowing these processors to see what is accessible to them. Now, this message passing is explicit. It has to be done, and this is supported in MATLAB. We're not going to get into that because it's for lack of time, but there is a way to do this, and there are MATLAB applications that can run in this way. Okay, but we'll be getting into is talking about GPU support within MATLAB. So what is a GPU? Often it's referred to more generally as a coprocessor, and that's a good description of it because it's an IC that lives on a separate card and has its own separate memory. This is a really critical aspect of GPU programming, because I may have a CPU program and I want to run things on the GPU. The first thing I have to do is I have to transfer my data from the CPU memory to the GPU memory. And so you see that's the DRAM in these two cartoons here. So I'm going to move that data over there. And then on this GPU, it's a very interesting type of computer chip, because instead of having these CPUs that you have, the traditional CPU has all kinds of wonderful circuitry to handle all kinds of different types of operations. They're very robust, and they can handle all kinds of sophisticated logic. The GPU has instead of just like, tens of CPU cores, it has thousands of very lightweight GPU cores. And by lightweight, what we mean is they really can't do a lot of sophisticated type of logic. In other words, a good example is any sort of branching. If you have a lot of if-then statements, that's not gonna function very well on these little GPU cores. What's gonna end up happening is there's going to be a lot of serialization of these cores, meaning they're not going to be able to execute at the same time. And so all of this parallelism that you think you're availing to yourself is going to be lost, and it's going to be very inefficient. However, if you have a lot of data, and you have to have a lot of data because there's thousands of these cores, and if the compute you want to do on that data is very regular, in other words, you want to just do almost the same thing, same set of operations on all these pieces of data, but all the pieces of data are unique. So each one's going to work on its own unique piece of data. Then the GPU can be a real game changer in terms of the computation you're doing. It can give you 1 to 2 orders of magnitude acceleration if you have the right application for it to run on and you implement it correctly. And so for that reason, GPUs have become extremely popular for a variety of applications that have this type of computational structure. So we'll get into what that is and how MATLAB supports it, but this is a really terrific option that we've noticed has become very popular on our cluster. So what does an interactive session with MATLAB look like? It's basically your standard desktop. As you see here, I can open this up on I think wherever you guys are running from. There's a very popular interface right now is called Open on Demand, and what this is a web-based interface into to launch interactive sessions on the cluster. And what's great about these interactive sessions is that they're agnostic to whatever the desktop the person has who's logging in, right? It's just a web browser. It's, you could be on a Mac, you could be on a PC, you could be on a Linux box, it doesn't matter. And then what you can do is you can launch this MATLAB session. The other beautiful thing about it is if you have an interactive session, maybe you want to have a MATLAB interactive session because there's a UI involved, right? And you got to enter in a bunch of parameters and you don't want to, maybe you just don't have the time or the to kind of get into the intricacies of running in batch mode. So what you can do is you can launch these interactive sessions, and because the desktop is all remote, you can detach from it and reattach to it at another time. So this is a wonderful new option, and it's great. But I do want to talk a bit about running these MATLAB jobs in batch mode because of the ability to run large numbers of MATLAB jobs simultaneously, which is very difficult from interactive. So here what I'm showing you is a Slurm job script, and some people are not running Slurm, some people are running PBS. That's okay. Whatever the scheduler and resource manager you're using is, the scripts will have a very similar form, which is that the top half of the script is going to be instructions to the scheduler over what kind of resources are being requested and for how long. Here's about the simplest script I could come up with. You basically, I'm asking for 1 CPU, and here for time, I'm asking for 4 hours. And this is sort of the syntax for making these requests. This can all be looked up online. There's 1,000,001 Slurm tutorials, but the basic idea is that at the top here, and I should say this first bin bash line is customary in all these just to establish what the shell is, but what you can see is that I'm making these requests, and the reason is because when I make these requests, I'm really telling the scheduler, I want you to allocate this resource, and the amount of time is telling it so it can be able to schedule my job amongst all the other jobs that are being scheduled. Now, to make this a MATLAB job, I have to then, in the lower half of the script, it's almost like the script that we would give to an actor, right? We're going to say to the computer, this is what I want you to do once you have the computer allocated. And this is what I would type in if I were there in person. And so the first thing I do is I got to link to the version of MATLAB that I want to run. So here, see, I say module load MATLAB 2020A. Actually, well, we've updated to 2021A, but we do keep lots of legacy versions of MATLAB around because every once in a while there's someone who has a MATLAB code that no longer runs on the new version, and so we keep these legacy ones around, and that's why you have to specify the version. If you didn't have this module load command, which links to the MATLAB executable, then you would get an error. Just when you try to execute MATLAB, it would say, I don't know what MATLAB is, error, so I don't know what this command means. And so that's why you need that first line. Now the next three, so these pound lines here are just comments. Okay, but I give 3 different MATLAB commands here. These are 3 different batch MATLAB commands. And they're not equivalent, but they all will do the same thing. You would never execute all 3 because then you would just be executing the same program 3 times. But I want to go through what exactly these are. The first 2 are what we have traditionally told people how to launch MATLAB non-interactively. What we tell them is, okay, you want to use the no display flag. And the no display means, I don't want you to launch this big desktop that you typically get with an interactive session. And then we give the no splash command, which means I don't want you to give that little orange wave when you come up either. Don't give me that thing. Now this less than sign here says, I want you to pipe in the file that I have written, my M file, into this MATLAB command. And so what it's doing is it's going to take this hello.m file that I've written, and it's going to send it into MATLAB, and MATLAB is going to execute it. And I don't have to be, there's no interaction present. I can just let this run. Okay, so that's one way to do it. And I say end the above M file with exit, because you want it to exit cleanly. And that the problem with this one, this version and the second version of running MATLAB interactively, is it didn't really exit with a 0 exit code, which was a bit of a problem. We always had to say quit or exit just to be sure that MATLAB would exit cleanly. This second version here is almost exactly the same as the first here, except it uses the -R flag, which a lot of people who run MATLAB not interactively were traditionally familiar with. All you would do is you would type into quotes here what you would enter at the MATLAB prompt if MATLAB had come up. So that's what -R does. And then -R would execute this. Now, lately, in the last few versions of MATLAB, they have this new -batch flag. And this sort of encapsulates the no display and no splash and -R into one flag with a bunch of other great things about running in batch. First of all, it's got an exit code now of 0, so it's going to exit cleanly. It suppresses a lot of other allocations, like for sort of memory allocations it was doing just for the interactive sessions that it no longer will do for batch. So it's slightly more efficient. I say slightly more efficient because there is one thing about MATLAB, is that if you're running really small codes, like this code I wrote, all it does is say hello and exit, and you'd think it would be able to run almost instantly. But MATLAB takes a while to come up. And whether you're running it in any of these versions, it's going to take, I'd say, a good 30 seconds to start up a MATLAB. That said, once it's going, it's going to be running. If you have a code that takes hours or days to run, it's going to be running on this compute node for you and going. But but the -batch is the optimal way to be running. Now, what I do is this file here. This is just a file that I've written, and I call it job. And then what I do is I can say sbatch job, and sbatch is going to submit this non-interactive MATLAB job to the scheduler, and then it's going to run, or it's going to be scheduled and hopefully eventually run, and then my job is going. I wanted to show you just a slightly different version of this script, and all this one's doing is it's going to be using lots of cores. I mean, one of the reasons I may want to run on the cluster is not to use one CPU, but use 28, so I can multi-thread my program and maybe run 28 times faster. Okay, so what I do is I say -N1, which means I want to be on one node, and then -n28, and now I'm getting 28 CPUs. Now, the other thing I want to do in the second half of the script is I want to be able to tell the node, hey, I want you to multi-thread where you can. And so sometimes we have to set certain environment variables in order to make sure that MATLAB is aware that it can multi-thread. Even though you've allocated 28 CPUs using the scheduler, it doesn't mean necessarily that the application knows that 28 are there. So this is a way to explicitly say, I've got 28 CPUs. Then all I do is I link to the MATLAB executable, and now I run. And I don't need this quit here, so I didn't mean to put that. But this is the way to run it in batch mode, sort of just extra secure exit here. But then I would submit the job like this. Okay, so let's shift a little bit to talk about why we use MATLAB. MATLAB is a very, very popular programming language taught to scientists and engineers, and it makes a lot of sense why it is. They have a lot of extensively developed toolkits. They have a lot of, this company has been around for a very long time. It looks like we're approaching 36 years here of having MATLAB around, and it's great. It has some of the signal processing matrix operations libraries. I think their visualization support is extremely good. And I will also add that if we were going to contrast it with these other tools such as R and Python, the one thing we could say about MATLAB is it is an industry supported code. It has MathWorks makes this application. And for that reason, there are certain quality to the way in which the software is made that that I think creates a lot of confidence in the product that is created. A lot of the toolkits have been, there's a lot of quality control that's being done. And for that reason, there's a lot of appeal there. As with all these tools, though, whether it's Python or R or MATLAB, there's always the critique we hear that these are interpreted codes, that somehow if we wrote this all in a compiled language like C, we would be seeing this, there's this belief that there would be this massive acceleration that we would see just by compiling it. But it's never quite that simple. I mean, yes, writing interpreted code, and by interpreted, what we mean is that we type in, we have human readable commands that we enter into our program. And then at runtime, those human readable lines have to be interpreted into machine language and run. Versus, let's say, a language like C, where we write the human readable language, right? But then we run something called a compiler, and the compiler turns it into binary, and then the binary is executed immediately. The thing that we have to understand is that while yes, there is, the code is interpreted, the code that's interpreted in itself invokes binaries under the hood that were written in these highly efficient LinPack and IcePack and all these other binary matrix libraries that are highly efficient. And if we were to write MATLAB in the right way, we could see extremely good efficiency in the way that it runs. Conversely, it is very easy to write highly inefficient MATLAB code that runs very slowly. And so when we're making these comparisons to compiled code, we just have to be sure that, hey, are we comparing well-written MATLAB or poorly written MATLAB when we're making these comparisons? But I should say that MATLAB has an amazing ability to run very efficiently, and that's why people who use it are very happy with it. And it's very widely used on scientific codes in a variety of spaces, be it national labs, universities, or industry. Okay, why would we run it on a MATLAB? Well, number one, if we wanted to run lots of jobs, like I was talking about before, doing a giant parameter sweep. If we have a lot of memory demand, because on clusters, there's typically a few nodes that have a very high amount of RAM. We're talking in the terabytes available to run. Sometimes we have just enormous data structures. And of course, when these data structures, if we can fit them into memory, then the compute can run on these, and it can be and it can execute very efficiently. Third is running on GPU. Although people may have GPU cards available to them on their our desktops, typically a lot of these clusters, what they have are not just lots of GPUs that are available to run on, but sort of these industrial grade GPUs like the V100 or the A100, which have a large number of compute cores available, and maybe more importantly, a larger amount of GPU RAM available. So as I was mentioning before, the GPU has its own memory. Oftentimes that memory is not at the scale that you get on the CPU side. So just to give you some numbers, I mean, forget about these high memory nodes where I was saying you have a terabyte of RAM. Just on a typical node with 28 CPUs, you may have like 128 gigabytes or 300 gigabytes of RAM available. On the GPU side, typically with a V100, what we're looking at is 32 gigabytes of GPU RAM. With the A100s, they are now offering 40 gigabytes or 80 gigabytes of GPU RAM. So that's sort of the numbers we're looking at for storing our data sets. Another reason you may want to run on a cluster is because sometimes, like at our university, we've paid for licenses to very specific MATLAB toolboxes that would be available there. We have a multi-precision toolbox. We have some researchers who are very interested in running not to double precision or quad precision, but to really high levels of precision. Oftentimes you need to do this if you're looking. The really interesting part of your computations are many decimal points down in the computation of a number. And so these are the kinds of things that might be available. And that I should say there are a lot of specialty toolboxes made by third parties that run with MATLAB that are really spectacular. And that's another reason you might run on the cluster, is to just avail yourself of those resources. Then there's the multi-threading, which is a big appeal, because that is sort of your, we'll call it, your easiest way to accelerate codes, usually, not always, unfortunately, but and so multi-threading, especially if you want to, there's a larger number of cores per node typically on these clusters, and that's why that's appealing. And then there's the big data applications, which we'll get into. Okay, so let's say we had our MATLAB code, we brought it over to the cluster. And now what we want to do is see, okay, where do I need to tune this thing? Where do I need to find the opportunities for acceleration within this code? So just like as you might do for lots of other types of codes that you're profiling, sometimes the simplest thing to do is just to stick in timing statements throughout the code just to see where the times are. And MATLAB has a great tick-tock function. Really simple. You put tick in one spot, before a piece of code, you put tock after, and then you can print out the time it took for that block, and then you can do another tick and tock and do those ticks and tocks all the way through the code. And you can profile it, and it's cheap and dirty, and maybe if you really want to get into doing profiling effectively, you probably need to move beyond that. But I think as a first blush way to look at where you need to focus your efforts, it's great. If you are multi-threading and you're kind of concerned with the transfer of data between the different processes, there's another version of tick bytes and talk bytes. Of course, it's not really time related, it's more data related, but that's another tool that's available. I want to talk a little bit about the MATLAB profiler, because it is a really nice tool. It's super easy to use, and it's really well developed. And here's how you use it. You just simply type at the MATLAB prompt profile on, and it's going to start profiling your code. And then you can, if you're interactive, you can turn on the profile viewer just to see how the code ran and where all the time was spent. And it's a bunch of links. It starts off at the top level, and it has a list of all the routines that were run and where the time was most spent. And then you can click on these. They're all hyperlinked, and you can click on those, and then you go deeper and deeper into the code to see where the time is most spent in the program, and it does all this profiling. Now, if you're running in batch mode, you could just turn profile on, and then when the program's ending, you can type prof save, and prof save will store everything in a directory in that run directory, and the directory is called profile results. And if you go in there, you'll see hundreds of HTML files. And so if you just copy those over, or you can view them, actually within the interactive session. Then you click on file 0.html, and that will be the top level of the profiler, and you can click through it all and see where the time is spent. So that's another great option into looking into your code. All right, so let's talk about now best uses of MATLAB, and these are going to be pertinent to anybody who's running MATLAB, whether on a desktop or on the cluster or anywhere. Just really simple. Just tips to kind of immediately get some better performance. So the first thing is pre-allocation. MATLAB doesn't, unlike languages like C, you don't have to allocate arrays. Now, that's a great convenient thing on the one hand, but on the other hand, it's a huge opportunity for real huge inefficiency. So here what I have is a code on the left and the code on the right. These two codes do the same exact thing. Okay, they're going to take an array X with 1 million elements, and it's just all they're going to do is it's going to iterate through a for loop, and it's just going to add 5 to the previous element in the array. Now, what you see here is I allocate X1, the first element of X, to 0. I say, okay, my first element is 0. So that way, every iteration through this is going to build on that. It's going to just count by 5s. Okay, and then this loop is going from 2 to 1 million. But what's happening here in this line is that every X of K, see, X2 it's not only setting the value of X2 here, it's allocating the memory for X2. And as you can see, it's going to do 1 million of these allocations. Well, these allocations take buku time. Okay, when I do the tick and tock, it says to me at the talk, it gives at standard out, it says elapsed time is 0.3 seconds. If I simply pre-allocate X, all I'm doing here is I'm just saying, give me an array of zeros that's 1 million long, and do the same exact loop. The elapsed time is 0.01. In other words, I'm getting a 30-time acceleration, well, almost 30, times acceleration simply by doing this pre-allocation. So that's big. All right, but there's other things we can do. Okay, now in these previous loops, I should say the one thing we gotta be aware of is that each of these iterations is dependent on the previous iteration. In other words, I need to know what is in X1 in order to set X2. And similarly, I got to know what's in X2 in order to set X3. So there's a dependency between my iterations, which means I can't multi-thread it. You probably could actually multi-thread this, obviously, but the point is you couldn't multi-thread it using this code. But there are other codes that are more straightforward in what they're trying to do. For example, if you look at this code here, and these two codes again are totally identical, the left and the right, what they do. Okay, but here I have a for loop and here I don't. So let's talk about what that means. So here I'm doing, I'm counting by 0.01. So this is a loop over 1,000 elements. And I'm iterating and I'm saying, hey, can you, then I have this integer I. And all I'm doing is taking the sign of t and storing it in yi. Okay, and the presumption here is that I pre-allocated y up here. I didn't have to do, but let's just say I did. Okay, but either way, I'm storing sign of t. The problem is sign here is operating on a scalar. T is a scalar in this iteration variable. But if I preset t to be an array of 1,000 elements, right? So now t here is an array. It looks the same, but it's not the same. Here t is a scalar, here it's an array. And now if I just say y equals sign of t, instead of running sign on a scalar, I'm running sign on a vector. Okay, and because I'm doing that, the compiler, or I should say this runtime interpreter is able to know that I can do multiple values of t and calculate multiple values of y simultaneously. What does this look like at the hardware level? If you look down here, what's happening here on the left is that because it's iterating sequentially here, it can only fill these registers partially. It can only fill a quarter of this register. You see, but if I run it this way, it's able to fill the entire register up, and so I'm getting a 4 times speed up. It totally depends on the lengths of these registers and the data types we're working with here. The register could actually be a lot bigger, but all I'm trying to say is you just by switching from a for loop to running in a vectorized way, you can get a multiplier of acceleration on these things. Now, implicitly, what I'm sort of saying here, well, actually, let me just make it explicit. You really want to move away from for loops in MATLAB. I mean, in general, where you can, because anytime that you can take advantage of this vectorization, you should do it. Now, I'm going to totally contradict myself later when we start talking about par4, because par4 is a for loop that we're multi-threading. But I would just say that these situations are going to vary. Where there's opportunities to vectorize, you should do it. Where you can't vectorize and you have a for loop that is still parallelizable, we'll use par4. But this is sort of these are the sorts of code deciding decisions that you have to make as you are profiling and trying to optimize your MATLAB code. And here's just another example of another thing you could vectorize. Here you see, and instead I can take the mean of A. I can, and then what you see here is there's another loop here where B is trying to do some normalization around the mean, right? Well, what we can do here is we don't have to do that. If you look here at the bottom, I'm calculating this value just by saying A minus mean. So this is another way to do it. A few other MATLAB tips that are really useful in just speeding up any MATLAB code you have. You don't want to use clear excessively. People back in the day, I love saying that, back in the day used to use pack a lot because it was a way to sort of consolidate memory. Nowadays, I think a lot of this is already handled and pack isn't very effective. Using data as code in general, really, well, when you're using a compiled language like C, these things are usually handled by the compiler for you. But in MATLAB, data as code is a big problem, especially if you have a large number of constants and big constant arrays that are set. Using the .mat file and loading that in is going to be way more efficient. So if you have a lot of this stuff in the front of your program, this is a great way to improve performance. With conditionals, there's a lot of if you've got a lot of conditions, There's great ways to vectorize those as well. There's an any and an all. These are ways of basically taking a ands and ors and basically vectorizing those. All right, now this next bullet about sparse arrays is actually going to be related to a lot of other types of enhancements we're going to see, but the sparse is a really important one. So when you have matrices in MATLAB, there are matrix operations you might run, right? You might do a linear solver. You might, and linear solvers in MATLAB, it's as simple as just using the divide operator. You could say, x is equal to a divided by b, right? Or you can use there's another divide operator where you use the backslash, and that's slightly more efficient and invokes a different set of MATLAB routines. But when you define, if you have a matrix and you know that it's sparse, by sparse, we're just saying that it has a lot of zeros, right? So for example, I1000, you see A is equal to I1000. What does this mean? I is just creating, it's just it's just a diagonal of ones and nothing else. So what you have here is a 1,000,000 element array, but only 1,000 of them are non-zero. So that's a sparse array. And if you can take your sparse array and you can convert it to this sparse data type, you see AS is equal to sparse of A. Anytime I invoke a function now in MATLAB where I want to do some kind of a matrix operation, and MATLAB is aware that this matrix is sparse, it is going to automatically invoke implementations of these matrix operations that are very effective on sparse arrays. So it's sort of like you just have to tell MATLAB the data that it's working on, and MATLAB will invoke the appropriate version of that function for you. And this is going to happen. This is going to be a recurrent theme here, but sparse is a really big and important one to be aware of, because essentially what I'm talking about here is you're just trying to avoid MATLAB doing tons and tons and tons of needless computations on zeros. That's all we're trying to do here. And sparse is the way to avoid that happening. Okay, and then this last bullet I'm going to really get into, because there is already concurrency probably implemented in a lot of these routines already. And so all we have to do is avail ourselves of it, and we may be able to see acceleration without changing our MATLAB code really at all. Okay, before we get into that though, let's get back to talking about how would we run a large number of MATLAB jobs doing like a parameter sweep or something like that. So SBatch, we used SBatch job to submit our job, but there's actually a flag we have here called the -- array argument. And what that does is it takes a series of numbers. They can be comma separated, you can have a dash, you can do whatever you want. And what this is going to do in this case is it's going to launch 21 jobs, because it's going to go from 0 to 20. 21 jobs are going to get launched. Now, you may say, well, 21 jobs, but are they all identical? Well, no, they're not. They're not identical, and here's why. Because in the job, and here all right, I got to fix this. I was showing you guys the -batch flag before, so this is something I got to, but the -batch flag would be used here. But what I'm doing here is I'm invoking it. I have an M file called project1, and then project1, I'm passing in this variable called slurm array task ID. Slurm array task ID, for every invocation of this job that's been launched, this job array that's been launched, each one of them is going to have a unique value for slurm array task ID. So each one's going to have the value 0, 1, all the way to 20. And so I'm launching these jobs all with a unique argument. And then in my M file, in this project1.m, you see I can pass in an argument. This is how you do it. You just say function equals, you see project1, and then arg1, and arg1 is going to be one of these integers. And in this way, I can implement a parameter sweep. Now, there's a few things we got to be aware of when we do a job array like this. The standard out is all going to be unique and saved in separate files. But we just got to make sure that if we do write an output file from here, that we probably want to have a file name that incorporates slurm array task ID into it, so we're not clobbering all the outputs from these different MATLAB jobs. But if we can handle that, and this is a really great way to launch. If you want to do hundreds or thousands of these things and just submit them to the cluster and let them all run, this is the way you would do it with MATLAB. Okay, part 4. what does it do? It multi-threads for. So there's a few arguments you got to learn to run this. Par cluster is a great command because it's a way of sort of querying the system and finding out how many threads there are. In this way, you can parameterize the par pool, right? Because then you could just say, okay, I want you to start a pool of however many threads I've allocated in my SBatch script. So that's what, and so here I'm explicitly saying 28, but I could say a par pool with the value the par cluster returned, which I've stored into some variable. Let's call it num CPUs. So I could start it that way, and then it would start a pool with that many threads. Now, if you don't use either of these and you just want to run par4, par4 will start up and multi-thread automatically with a default par cluster. So it's going to default, it's going to come up with, it's going to use whatever defaults are there. We're going to talk about what these defaults are, but there is a way to sort of just change your for to a par4, and it will run multi-threaded with whatever the defaults that are available. But if you want to explicitly set these things, which I'd recommend, just so that these things are, you know what's going on with your codes, this is how you would do it. Now, we've been running MATLAB, and people who have been running MATLAB on our cluster for a number of years, and we've picked up a few, gotten a little wisdom over the years. So I just wanted to share a couple of these tips. The first is this. If you are submitting multiple jobs, so let's say you do a combination of both things I've shown you now, the submission of the Slurm array and running a par4. And if you're doing this with large numbers of jobs, there's actually a conflict that can happen with MATLAB trying to allocate it's trying to lock a specific file that it creates. You don't even have it. You have no idea that this even exists most of the time until you try to do this. This lock problem happens, and then all these jobs start to fail. The way in which you can get around this is by making a temporary directory based on your Slurm job ID. The Slurm job ID, this is just an environment variable that is created as soon as you submit a job using SBatch. So you just what we do is we tell people just create a directory, with your ASU write is our way of saying your login ID. Okay, and then you create these directories, and these directories are now used inside. You see, it says PC. So I'm using the par cluster command, and then I create my par cluster, and then I can set a variable called the job storage location, and I set it equal to that scratch directory. You see, so it's gonna in the M file, it's gonna use this as my job storage location directory, and this way we avoid the locking conflict, and then you can submit lots of parallel par4 jobs. Lots of batch par4 jobs simultaneously. This is a way of circumventing that problem. The other thing we've learned is in your directory, you have a .matlab directory. This dot means it's like a hidden directory. And in there, you want to go into this local directory here, and you just want to clean it out. There's tons and tons and tons of sort of bookkeeping type of files that are stored there, and they're never cleaned out. And so it gets really, really big. And eventually it starts to create performance problems. So just go in there and delete everything. Not when your jobs are running, of course. Because then you might affect an actual running job. But when nothing's running, just delete it and clean it out. And it tends to remove all kinds of issues that people are seeing with these jobs. Okay. There is if you have MATLAB Parallel Server, there is a script called config-cluster.n. You only need to run it once. And what it does is it creates two separate ways to run par4. One way to run par4 is with this. This one's called the Gabayar 2020A, but you'll probably have a different kind of default profile. But what this allows your par4 to do is to submit lots of jobs to various available nodes on the cluster. It sort of distributes your par4. Otherwise, you can run it with local. And I think the way par4, I typically have seen it run most efficiently is with the local. What you do is you just say, I want to allocate these CPUs on this node, all of them together. I want to run on the local, and then that way all of the iterations of your par4 can see the same memory. And so you're running in the shared memory paradigm versus the distributed one. And it's a lot more efficient. That said, you may, if you have lots and lots, if you want to run lots and lots of par4 iterations, and each of these iterations is very time consuming, the default configuration of the cluster may be a better way to do it. So here's how I'm going to launch a par pool. Here I say par pool, I name the local cluster, and I say 6. So I've allocated 6 CPUs. And here what you see is I do a par4 and it's going to just do this computation, but it's going from 1 to 200, but it's distributing among the 6 CPUs I've allocated. So this will probably accelerate close to 6 times this type of computation. It's a nice beefy, it's doing a rand of an I give a rand of an absolute of a max. So it's doing all these things, and it should be. And then so if you ever want to do clean up after your par pool is done, you can delete the cluster if you want to. Otherwise, when the program ends, it'll remove this stuff. Now let's talk about the built-in parallelism. There's 2 ways. So the best way to find this stuff is if you go to the mathworks.com site and you go to the support tab and you go to and you click on functions. In the lower left panel, you will see this set of check boxes come up. And so if you go to functions, it's going to give you this massive list of every function available in MATLAB and every available toolkit. But if you go to this lower left corner and you check the automatic parallel support box, this is an old capture. I'm sure there's way more of these now. You'll see there's a whole bunch of functions that have automatic parallel support. And what that means is you might just be able to say something like, using some function, you say use parallel and true. And now all of a sudden you don't have to worry about par4 or par cluster or any of that stuff. It's going to run that for you. So this is one of those things that's available. But let's look at a par4 and what's involved here, because there's a lot of rules for par4. I'm really pushing it with the time today. Okay. So just to briefly go through this, so you've got these iterations. There's different types of variables that are in these for loops. So for example, A is a temporary variable. It's only going to exist once in these iterations and then never be used again. It's able to identify this. Z is a reduction variable. What this means is I'm going to try to sum over all the iterations of this loop and store them into a variable Z. Well, MATLAB is able to identify, despite the fact that you are running these iterations in parallel, that it needs to collect subsums of Z and then total them up for you and produce the reduced value of Z for you at the end. Arrays are very special. Okay, on the left side, I've got a sliced output variable, B, and on the right, I have a sliced input variable, R. And so what it's going to do is it's going to be able to partition these arrays, and I mean, it's going to be able to address these arrays simultaneously, but there are specific rules for slicing arrays with MATLAB, with par4 that are very unique. And finally, C is what's called a broadcast variable. All the iterations share it, but it's not written by anybody. Okay, first of all, rule number 1 with a par4, you cannot have an iteration depend on another one. So here AI is depending on AI minus 1. MATLAB will tell you, if you try to do this, MATLAB will say, I cannot do a par4 on this. So MATLAB doesn't, if you were doing something like in C with OpenMP, it would just let you do this stuff and you would just get garbage. MATLAB won't even let you do this. It'll give you an error. You can't do any eval C, eval in, any of this inside of par4. It won't let you do that either. Third, the loop variable must be increasing integers. Any of these fancy stuff you saw, like I did before, where I was increasing by 0.01s, it won't let you do that. It won't even let you use decrementing integers. So you got to use increasing integers. Now, granted, all these things can be, rule number 3 is easy to circumvent, with a temporary variable, but this is how the outside loop variable has to function. And lastly, you can't do, or sorry, I shouldn't say lastly, rule number 4 is you can't reshape variables. You can't do any of these kinds of things where you're adding onto the end of an array. All this stuff is not allowed. Everything has to be pre-allocated that you're running on. The last one has to do with slicing, and this gets a little bit complicated, but basically what it has to do is when you have 2-dimensional arrays, you have to have specific ways of addressing them, or the par4 doesn't know how to do that. And I provide here, I think these slides will be provided to everybody, but there's all kinds of advice on how to work with 2-dimensional arrays in a par4 loop. All right, SPMD is just a more generalized version of a par4. What you're doing here is you're running lots of statements in parallel. But in order to identify what the threads are, you don't have an iterator anymore. So you can use a variable called lab index, and lab index will have a unique value that an iterator would. And then you can run all kinds of statements in simultaneously. All right. Distributed arrays. So MATLAB provides a lot of support for running things in taking very, very large data sets and being able to partition them in an efficient way. Can't get into the distinctions between distributed and co-distributed now, but do realize that there is some there is great support for being able to do data parallel operations that doesn't do any sort of duplications of data. All right, well, okay, and then there's this ability to handle really large data sets with something called the data store. Here what you see is there's a dataset.csv. We're able to load in only specific columns from this data store into our data, into memory, and operate on those. So this is a nice functionality that you have. And tall arrays are really just, you have millions and millions of rows now, instead of, so the previous case we had maybe millions of columns. Here we have millions of rows. And this is a way, the tall data set is a way to sort of be able to access these. Now, the one thing to notice in all of these that is, just like we were casting the matrices as sparse, you can cast data sets as distributed. You can cast things as tall, and immediately MATLAB knows how to invoke the functionality it has to operate on these types of data structures. Okay, this is about batch submission for MATLAB. I'm gonna have to skip ahead on this one, but basically this is a way in which we might be able to submit jobs from within a MATLAB session. I wanna get into GPU. Basically, this is yet another type of casting of variables, is really the best way to describe this. So here what I have is I've defined, in this example, I think we'll be able to capture this. Here what I have is a D. D is a magic array. That just means it's a 1,000 by 1,000 matrix where all the rows and columns sum to the same number. But this is a 1,000,000 element array that I've created on the CPU side. Simply by defining an array called A, which I've cast as a GPU array of D, what this does is a transfer of the data, the 1,000,000 elements, from CPU memory into GPU memory and stored it into GPU memory as A. The point is that when I run the FFT function on A, FFT is running the GPU version. This is the GPU implementation of FFT, and that's going to store that in F. Then if I say gather F, this is going to take the GPU result that's in GPU memory and store it into a CPU data called F. And now I can do a comparison between an FFT that I ran on the original. This is a CPU implementation of FFT that's running on D, and I'm subtracting and finding the norm. So there's all kinds of great GPU functionality that's already there. Once again, you could do the same thing. You could do either methods GPU array and find a list of methods, or you can use those checkboxes that are over there on the MATLAB site, the MathWorks site that I pointed out before. Oh yeah, here's a picture of it. So look, this is an old screen capture, but you see GPU arrays. I can check this box here. So automatic parallels, well, here's GPU arrays. So there's 679 functions that I could check on that could see if I have a GPU implementation. It's that easy to run GPU functions on in MATLAB. That said, writing it efficiently, that's going to be another story. All right, I can't get into Next compiler and doing this, but only to say that you can do this. You can write your own parallel codes, whether they're in CUDA or they're in C, and you can write them to be run by MATLAB. So I will just jump ahead through all this next stuff, but only to say thank you it's been a pleasure to participate in the Research Bazaar this year. I will make these slides available for upload, and hopefully if there are any questions, please feel free to reach out to me. I don't know if there's any quick questions. I could field those now. All right. Well, thank you, everyone. This was great. We'll I don't know. On to the next sessions, I suppose.
Okay, I'm going to stop the recording now.